Hello everyone. So today what we're going to do is we're going to start on 10.3 linear equation. So it would be probably our first section where we actually talk about differential equation that you haven't learned how to solve yet. So if you think about it, in 10.1 we did talk about two different type of differential equation, but you already know how to solve those from basic calculus. So let's start. So we're going to define a new type of differential equation. So a first order linear. So here's the big word. We didn't use this word before. Linear differential equation is a differential equation in the form of y prime plus g of x y equal to f of x for some functions f of x and g of x. Oops. So it's called first order. So we already learned what first order mean. That means it's only up to the first derivative. We obviously know what differential equation mean. So the word linear here indicate that the following indicate that you have y prime and y, but you don't have any functions of y or y prime, nor do you have any multiplication involve y and y prime. So I know some of you probably thinking like, well, but what happened to g of x? Well, g of x in this case acts as a coefficient in front of y. As long as this coefficient is not a function of y, it can be a function of x. It's okay. Okay, so these sort of equations are one of the most basic differential equation that you can learn how to do, and there are basically three distinct cases that we can consider. So what are these three distinct cases? So let's start with number one. Number one, if g of x is equal to 0. That's our first case. If g of x is equal to 0, that would mean that our equation becomes just y prime equal to f of x. And that is a direct integration problem. Oops. And the solution would be y would equal to the integral of f of x dx plus some kind of constant c. That would be how the solution set will look like in this case if g of x equal to 0. Now, case number two will be, what if f of x is 0? If f of x is 0, this equation actually becomes what we call homogeneous equation because of the fact that it's equal to 0, the equation. So this equation actually will turn into that. So it will turn into y prime plus g of x y equal to 0. And this is a separable differential equation. Why? Because you would do the following. You will actually move the g of x y to the other side, and then now divide that the y to the other side. And now it becomes separable. So now what happened to this separable differential equation? Well, we can definitely look at and try to see what the solution set would look like. So I can just simply try to solve this equation. So if I do that, I will notice that on this side, what I have is the following. I'm going to rewrite y prime to be dy over dx. And I'm going to separate dy and dx. I'm going to integrate, so that becomes integral of absolute value y equal to negative integral of g of x. Oops, I write the wrong letter here. dx plus some kind of constant c, of course. And so now then what I'm going to do is I'm going to just raise it to e power. So I'm going to do this here. So if I raise both sides to the e to that power, it just become y equal to some constant e to the negative integral of g of x dx, where the plus c part become the constant in front, and that constant can be positive and negative, which take care of the absolute value sign. So that's how the solution will look like if f of x is equal to 0. So both of these you know how to do. So now come the final scenario. What if neither f nor g what if neither f of g is, oops, here we go. What if neither f of g is equal to 0? So that's case number 3. Okay. If, let's say, f of x is not 0 and g of x is not 0, then what we need is, it will require a new method to find the solution set. So what's this new method that we're going to be doing? Well, this new method is called exponential integrating vector or exponential multiplier method. Or sometimes I refer to as exponential multiplier method. EMM, sometimes I call that. If you think about it, it's kind of the same thing, because exponential integrating factor, the word factor meaning that you part of a multiplication, that's why it's called exponential multiplier method. So show you how this works. Okay, so the way it works is the following, is that you would start with the equation. Let's say y prime plus g of x, y equal to f of x. Usually this is referred to as the normal form of the differential equation. So what does it mean by considered to be normal form? Is when you have all the unknown function and the derivative. So in this case, meaning y and all the derivative of y, which is y prime in this case, all on one side of the equation and anything else on the other side. So notice that on the other side is f of x, which is a function that involves only x but no y involved. And all the y, which are an unknown variable, and its derivative are all on the left-hand side. And some of these y might have some coefficient in front of them, and that coefficient could be a constant, it could be a function of x, it just cannot be a function of y. That's all. All right, so it's called normal form. So how does it work with this? So it's obviously called the exponential integrating factor method. So therefore, we need to define what we call the integrating factor. The exponential integrating factor for this equation is basically given by this function. We're going to call this exponential integrating factor or exponential multiplier m of x. And m of x is defined to be e to the integral of g of x dx. Okay, so m of x sometimes is referred to as exponential multiplier. Oops, not multiple, multiplier. Which is the reason why it was also called exponential multiplier method. So how do you use this exponential multiplier? Well, as the name suggests, it's called multiplier. So to use this multiplier, what we're going to do is simply to multiply the entire equation by this multiplier. So once we find m of x, we will multiply the entire differential equation by m of x. Now, it might seem like, wouldn't that make the equation more complicated after I multiply it by the exponential multiplier? And you are right. It actually does make it look complicated. But, of course, there's a reason why we do that. So let's see what happened here. So I have y prime plus g of y, g of x y equal to f of x. So here's my exponential multiplier. So I'm going to take this. I'm going to multiply to the entire equation. And what do I have would be the following. I will have e to the integral of g of x dx multiplied by y prime plus g of x e to the integral of g of x dx y equal to f of x e to the integral of g of x dx. Maybe I put parentheses around here, make it look nicer. Okay, let's get this out of the way. There you go. Now, yes, you're correct. This equation definitely looked way more complicated than before. So why would we want to do that? I mean, I know I always tell you that mathematicians like a challenge, but like, wouldn't this be like a little too challenging? At first glance, it might be, but as a matter of fact, hopefully the purpose of doing that is to recognize the following. This side of the equation, this side, is actually a result of something that you learn back in BC calculus called the product rule. So some of you who are my students probably recognize when I taught you guys product rule, I told you that the product rule is 1 d2 plus 2 d1. And I'm going to have to rearrange the order because of the way that I wrote it. So therefore, if you look at this, this is our 1, this is our d2, and this is our 2, and this is our d1. And if you think about it, it makes sense, because if the derivative of e to the integral of g of x dx is actually equal to g of x e integral of g of x dx. Because of chain rule, you have to take the derivative of the integral of g of x, which the derivative of the integral of g of x is just g of x. Okay? You know what? Let's see. Oh. Nope, that's not what I wanted to do. There you go. All right, we'll move it closer. So that way it's not all the way at the end. All right, there you go. Much better. Okay, good. All right. So therefore, meaning that this whole side right here is actually just the derivative of product rule. So it will be e to the integral of g of x dx multiplied by y. And that technically equal to f of x e to the integral of g of x dx. Now, of course, the idea here is the following, is that once you get to this point, then you hopefully be able to solve for y by integrating whatever is on this side of the equation, and then be able to somehow divide out the exponential multiplier. So let me show you in an actual problem how does that work out. Okay? So let's do a very simple problem just to show you how that works. Okay, so how about we have this equation right here. Let's say dy over dx is equal to y plus 1. Let's solve for y. Okay? And after I solve for y, we're going to say let y of 0 equal to 1. Find the specific, oh, actually, maybe I should say it this way. Solve the initial value problem. Okay? So let's try to solve for y first. And when we have y, we can then try to solve for the initial value problem. So how do you go ahead and how do you solve this? So first I'm going to do is, I'm going to rewrite it as y prime equal to y plus 1. And then I'm going to go and put it into what we call the normal form. And yes, you do have to put it into the normal form, because if you don't, you will not be able to identify the function g of x correctly. So now I'm going to look at this compared to the normal form of a first order linear differential equation. And based on that, I can see that g of x is equal to -1 and f of x is equal to 1. So now we really don't need to know what f of x is, but I do need to know what g of x is, which is -1. So therefore, that tells me that our exponential multiplier, m of x, would equal to e to the integral of -1 dx. And therefore become e to the negative x. And nope, you don't need the plus c, because the plus c would just basically confine into a constant in front. And as a matter of fact, you could actually put a number in front of e to negative x and it will work out exactly the same, because you basically multiply the entire equation by that, and so that constant would eventually just divide it out anyway. So therefore, we purposely choose, in this case, in this integration, after I do the m of x, I choose the constant to be just constant 1. And if you put a constant there, it will just divide out. So that's why we don't do it. So this is my exponential multiplier. So now I'm ready to solve my equation. So how do I proceed? Well, I'm going to multiply the entire equation by e to negative x. So therefore become e to negative x y prime minus e to negative x y equal to e to negative x. So here's the important part to realize the following. So I'm going to help you see this. So if I look at this, that will be e to negative x y prime plus negative e to negative x y. So notice negative e to negative x is a derivative of e to the negative x, and y prime is the derivative of y. So therefore, here's what they form: is 1 d2, and this is 2, and this is d1. So therefore, this actually combines into the derivative of e to the negative xy. That's the 1 and the 2 combined together, equal to e to negative x. So I'll write e to negative xy prime. So when I take the derivative of e to negative y, product will apply, and then therefore become e to negative xy prime plus negative e to negative xy. So now what I'm going to do is the following. Now that I have this, I'm going to try to figure out what y is. So what I'm going to do is integrate. When I integrate both sides, so the derivative of prime will just cancel out, and therefore just leave me with e to negative xy on one side, and then I can actually integrate e to negative x dx, and that actually integrate to negative e to negative x plus some constant c. So now that is kind of our general solution, almost. Now what we do is kind of write out the answer correctly. So what I'm going to do is try to solve for y. To do that, I'm going to write out the equation again. To do that, what I'm going to do is multiply the entire equation by e to the x, which will cancel out the e to the negative x. And when I do that, I'm going to have y equal to -1 plus, so here's the important part, c e to the x. c is any constant, but when I multiply by a function, it remains a constant, now become in front of the function. So this is now our general solution. Now that we solve for y. In some cases, we cannot solve for y, then this right here would be our general solution. But in this case, since I can solve for y, I would say this would be a better general solution. Now I need to plug in my initial condition. So I know y of 0 equal to 1. Therefore, meaning 1 equal to -1 plus c e to the 0. And if my math is correct, that become c must equal to 2. So now I'm ready to present my particular solution. So that is the solution that satisfies the differential equation and the initial condition. So this sometimes is referred to as a particular solution, subject to the initial condition of y of 0 equal to 1. So hopefully everyone see how that works. So now, even with this technique, this is actually definitely powerful because it allows us to solve a first order linear differential equation. The problem is, however, is this does require the use of integration, which I told you last time. We're going to try to actively avoid using integration to solve a problem because integration is hard. So therefore, meaning that this method only works if we can actually get through the two different integration involved. The first integration is when we try to look for m. And the second integration is when I realize that I have the product of the derivative. I have to then integrate whatever on the other side. So those are the two difficulty that we have to get past in order to use this method correctly. Now, give you another example very similar to this one. So let's say solve for y. And then here's our differential equation. dy over dx equal to xy plus x. Okay. So what we're going to do is, just like before, we're going to try to rewrite it into normal form, or normalized form. That will be y prime equal to xy plus x. And then I'm going to go ahead and move the xy over. So y prime minus xy equal to x. And some of you might be concerned like, wait, is x times y allowed? I thought we were multiplying two variables together. So here's the tricky part. The tricky part is that we actually not. Why not? Because in the sense of this kind of differential equation, the only variable that involved is, technically speaking, the dependent variable, which is the y. In this case, x actually acts as the independent variable, and as a matter of fact, in most cases, this x actually would act more like a parameter. We don't even consider that to be a variable. Okay? So now I'm going to identify what my g and f is. So here's my g. G of x is equal to negative x. Here's my f. F of x equal to x. But as I say, in this case, using this method, it really doesn't matter what f is. Okay, so now that I have my g, I'm going to go and find my exponential multiplier. Okay, that will be m of x equal to e to the integral of negative x dx, and therefore become e to the negative x squared over 2. So that is our m of x. Or sometimes I just simply go call it m, with it understood that being is the function of x. So now I'm ready to go and take that and try to use it. So here's my equation. Y prime minus xy equal to x. I'm going to multiply this entire equation by e to the negative x squared over 2. So therefore become e to the negative x squared over 2 y prime minus x e to negative x squared over 2 y equal to x e to negative x squared over 2. Notice that this right here is our derivative of this. And then y prime is the derivative of y. And technically speaking is plus negative x because of the negative x squared as a derivative, as the exponent. So now I can say that this will just be e to the negative x squared over 2y prime equal to x e to negative x squared over 2. And yes, if you're thinking like, oh, what go inside this derivative, what's the product rule going to be? It's going to be the exponential multiplier and y. Exactly that. Okay. So now that does require me to be able to integrate this part right here. So that would be kind of the tough part. So I'm going to go and write this first. E to the negative x squared over 2y would equal to the integral of x e to the negative x squared over 2 dx. And of course plus some kind of constant c. So now this actually is not an easy integration. So I'm going to go and try to do that separately. So integral of x e to the negative x squared over 2 dx. And so some of you probably recognize that how to do this integration. This is nothing more than just a u substitution problem. So we're going to let u equal to negative x squared over 2. Then du would just equal to negative x dx. Notice we do have an x, we just don't have the negative x. So what I'm going to do is I'm going to move it to the other side. So this become negative integral of e to the u du. And so that become negative e to the u. Well, plus c, but then I already have the plus c here, so I'm not going to worry about it. So that just become negative e to the negative x squared over 2. All right, so now I'm ready to finish. So that just equal to negative e to the negative x squared over 2 plus some constant c. And so now what I need to do is kind of solve for y. So what I'm going to do is this. So now I have this equation. So we'll go and multiply the entire equation by e to the x squared over 2, because that would balance out the e to the negative x squared over 2. So when I do that, I do have y on this side. And notice that these two things also cancel and leave you with a negative 1 plus c e to the x squared over 2. Now notice that solution looked kind of very similar to the last one that we did. And the reason why is because of the format of the function. Okay, and you'll notice that a lot later on. I'll explain to you how that actually play out. Okay. So the last thing I want to show you is this. The last thing I want to show you is maybe an example. Let's hope we have time to finish this, because I do want to just finish this last example. So if today's video is a little long, we probably not going to have a video for tomorrow, because this is probably a 2-day topic. So hopefully that would be the case. Actually, you know what? It's 28 minutes already. Maybe I'll stop right here and just do the last example in a separate video for tomorrow. And then tomorrow video will be really short. And that way you can still space it out. All right? Okay, so I will stop right here and I'll talk to you again soon. Okay? Bye-bye.